we aren't going to see any new types of functions over and above the familiar library functions that we saw in a previous video. And this is what I'm talking about with the linear, squaring, square root, absolute value, trigonometric functions, etc. Here we're going to look at algebraic combinations of functions. And algebraic combinations means addition, subtraction, multiplication, division, and composition. In all of these cases, we need to consider the domain of the function that we end up with. And when we consider domains at this point, what we want to do is we want to make sure that we have no zero denominators and no situations in which we have a negative inside of a radical, the index for which is even. Right? So like the square root of -3, we're not interested in that. The cube root of -3 is fine. So that's what I mean when I say even index. Well, down the road, you're going to be considering you want to have no negatives or zero inside of a natural log. That's not something we're going to think about at the moment. And adding, subtracting, multiplying, dividing functions is what you think it is. And we're just going to briefly refresh composition of functions. And we're going to do that using this example. For the given functions f and g, find f composed with g of x and g composed with f of x and their domains. F of x is given to be 2x minus 3 and g of x is equal to the square root of x. F composed with g of x is what happens when you take f and put inside of it g of x. The idea being whatever input I have would first go into g and then into f. And so g is the first function that the input will experience. And f has a rule that says 2x minus 3. So this would be like 2 times g of x minus 3. We can see here that g of x is equal to the square root of x. And so f composed with g of x is equal to 2 times the square root of x minus 3 with the square root of x replacing g of x. The domain here is going to be 0 to infinity. I gave that an interval notation, and there it is. G composed with f is the opposite, or it's the reverse order of composition. So g composed with f is going to be what happens when we take g and put inside of it f of x. Now the rule for g is to square root x. So this would be the square root of f of x. In your work, you don't have to write down this f of x there for 2g of x minus 3 and the square root of f of x. I'm just doing that so you know exactly what's going on here. But we know, folks, that f of x is given to be 2x minus 3. And so g composed with f of x is equal to the square root of 2x minus 3 with 2x minus 3 replacing f of x. Now going back to what we said about domains, we want to make sure we have no zero denominators, not an issue here. We want to make sure we have no negative numbers inside of an even root. And so here for the domain, we're going to consider 2x minus 3 needs to be greater than or equal to 0, which means that x needs to be greater than or equal to 3 halves. And I'm going to give the domain in set builder notation, so I'm just going to wrap the set of x such that around x greater than or equal to 3 halves. So what we have is the curly brace, the set of x, vertical line, such that x is greater than or equal to 3 halves. And then to give this the way I gave the previous one here, we'll say that that's the domain. And there we are. Next, we have one that's a little bit more interesting. Same instructions. Find f composed with g and g composed with f and their domains. F of x is equal to 1 over x plus 2. G of x is equal to x minus 1 over x plus 3. F composed with g of x is going to be, I'm going to write the structure of f 1 over thing plus 2. And in place of x, I'm going to put g of x. And I'll use a different color here. x minus 1 over x plus 3. So what we have is a big fraction 1 over x plus 1 over x minus, 1 over x minus 1 over x plus 3 plus 2, right? So 1 over fraction plus 2 is the denominator. Now right away here, I see that I have a fraction in the denominator of the fraction, and in that fraction, x minus 1 over x plus 3, I know that x cannot be negative 3. I can actually see that from g of x, right? G of x is telling me x cannot be negative 3. What about f of x? I'm not so concerned about that. That's going to come out later. The idea that I'm getting at here is when I have a composition here, f composed with g of x, when I consider the domain, I need to consider two things. I need to consider the domain of the inside function, and then I need to consider the domain of the result after I've simplified the expression. Now I just said simplify, and that's because this is a complex fraction. And so to simplify the complex fraction, I'm going to multiply numerator and denominator by x plus 3. So f composed with g of x is equal to, I have x plus 3 in the numerator, and in the denominator, in the first term, the x plus 3's will divide out, so I have x minus 1. And in the second term, I'm going to multiply 2 into x plus 3. So f composed with g of x is equal to x plus 3 divided by, combining like terms in the denominator here, I've got 2x plus x is going to give me 3x, and then I've got 6 minus 1, that's going to give me a plus 5. Now as far as the domain here, I know that 3x plus 5 can't equal 0 because it's in a denominator, right? So x can't equal negative 5/3. For our domain then, we're going to say it's the set of x such that x does not equal. Now, folks, we wrote down before that x couldn't equal negative 3. X still can't equal negative 3. Even though it's not a problem for the result, the idea is any number that I'm going to evaluate into f composed with g of x has to first go into g. And so I always have to be able to put it into the inside function. And then for the result, I got to make sure that x won't equal negative 5/3. So the domain excludes two numbers, one because of the inside function and one because of the result. Now, what about f? I know that the domain of f does not include negative 2. Well, let's look what would happen if we computed g of negative 5/3. For the numerator, negative 5/3 minus 1 is negative 8/3. For the denominator, negative 5/3 plus 3, or negative 5/3 plus 9/3, is negative 4/3. No, it's not. It's just 4/3. And that reduces to negative 2. And so by excluding negative 5/3 from the composition, we're actually taking care of the fact that x can't be negative 2 for f. So I say again, when we consider the domain of a composition, we need to consider the domain of the inside function and the domain of the result. We don't have to care directly about the outside function. Now, for these functions here, what I'd like for you to do is find g composed with f of x and its domain. Go ahead and pause the video and come back when you're done. All right, so g composed with f is 1 over x plus 2 minus 1, that's the numerator, over 1 over x plus 2 plus 3. Remember, we're putting 1 over x plus 2 everywhere we see x in the expression for g. I have a complex fraction, so I'm multiplying numerator and denominator by x plus 2, and the resulting algebra leaves me g composed with f is equal to negative x minus 1 over 3x plus 7. As far as the domain, we need to exclude anything that makes f's denominator equal to 0. So x can't be negative 2. And then here we need to consider the denominator of the result. And so x also will not equal negative 7/3. So the domain is the set of x such that x does not equal -2 or -7/3.